Hello, we're back for the Tuesday/Wednesday installment of Math 341. Hopefully, so maybe not by the time this video is posted, but certainly by Wednesday, your online assignments will be graded. If anyone is having submission issues or anything like that, please do let me know by email, okay? Also, you may notice the grades are probably a little on the high side. I want you to think back to grade school, to that kid. Remember there was that one kid, who would raise their hand and say, well, miss, didn't you maybe give us too many points for this? Shouldn't we all have not gotten this right? And at that moment, you, in a moment of reflection, you kind of thought that maybe adults weren't being honest with you when they explained that murder was bad. Maybe they hadn't come clean with you. Don't be that kid, okay? Yes, so assignments have been graded. Submission issues, talk to me. So again, after a little more back and forth with the department, everything is, kind of fluid these days, needless to say. But the plan does remain that the exam will be available for a whole 24-hour period. Okay, so it will be posted, and it will have a submission time exactly 24 hours after it is posted, okay? And I will tell you when the release time is, okay? And that will cover all possibilities, hopefully, for time zones. That will cover any concerns about extended time for people. And hopefully that will be enough time for you to overcome any internet or connectivity issues you might have. And I will be carefully monitoring my email during that period, okay? Although I would say that, as is the case when I'm there in person, I'm not big on answering a lot of questions unless there's actually a typo in the exam, in which case I will say something by mass email. All right, so I think that's the administrative stuff out of the way. I hope you're all well. Last time, we were talking about this location of roots theorem, right? So, briefly, right, so f, we wanted to show that you have a continuous function, f, from a closed bounded interval, and you have that f at a is strictly less than 0, is strictly less than f at b. Then there exists a c in the interval from a to b such that f of c is equal to 0. Okay? So there has to be a point where this continuous function crosses the x-axis. And then again, at the risk of repeating myself, I'm going to draw a little picture to remind you of the rough idea of the proof. And then today we will go into the details, the gory details of the proof, right? So we're going to have this function, f, which at some point crosses the x-axis, right? F at a is strictly less than 0, f at b is strictly greater than 0. And the idea of the proof is to repeatedly subdivide this interval, okay? We're going to chop the interval in two, and we're going to pick one of those two halves as the half that we have going forward, and then we're going to repeat this process. So you pick the midpoint here, right? Call that P1. And the first thing you do is check, is f at P1 equal to 0? if f at p1 is equal to 0, then you can stop. You can say, well, p1 is equal to c, and f of c is equal to 0. We're all done. If not, you have to choose one or the other of these two halves of the interval. And the way in which you choose it is that you choose the subinterval which still has the property that at the left-hand endpoint, the function is strictly less than 0, and at the right-hand endpoint, the function is strictly bigger than 0. And it is necessarily the case that if the function at p1 is not 0, then one of these two intervals will have that property, okay? So we'll start with this big interval being I1 from A to B, that's I1, and then whichever of these two intervals happens to be the one where the function crosses the x-axis, in this case it's this guy over here, that'll be I2. And then we're going to subdivide that guy again, find the midpoint P2, and maybe in this case we get super lucky. Looks almost like f at P2 is actually equal to 0. In that case, that's where we stop. F at P2, well, P2 is equal to C. F at C is equal to 0. We're done. If, on the other hand, the function doesn't quite cross the x-axis there, it does something like this, then we have to pick one half or the other here, and the one we pick is the one where the function crosses the x-axis, which would be this interval here. Okay, and that will be I3, and so on. So either at some point this repeated bisection process terminates and the function just so luckily happens to be equal to 0 at one of the midpoints of these intervals on the way down, or the process never terminates and we will get an infinite nested sequence of closed bounded intervals, and we will explain then how to use that infinite sequence to produce this point C at which the function is equal to 0. Okay, so again, that's the theorem. There's a rough heuristic idea of the proof. Oh, and incidentally, I sincerely hope that wherever you are, it's actually spring, because here, it's not spring. I mean, it's been freezing every damn morning. I mean, I already hate running. Running in the freezing cold is just miserable. And now I have to run in the freezing cold in the dark, because at 8 a.m. I have to start the 4th grade again. I don't know if this has happened to anyone else, but I've sort of like, I'll make whatever the kids want to eat for them. But for me, I've gotten to the point where I'm living a post-meal life. I don't eat meals. I just feed. It's like having a trough or something. It's disturbing. I need some regularity back in my life. Okay, so this is the proof, officially. So suppose f at A is less than 0 is less than f at B. And we will set interval number 1, I1, to be an interval whose endpoints we will label as A1, B1, and for starters, that will just be the original big interval A, comma, B. Okay? And then, as in the little heuristic picture, right, I then want to identify the midpoint of this interval. So set P1 to be the midpoint, and that's just going to be the average of A1 and B1. Okay? Then, like I said, if f of P1 is equal to 0, we just set C equal to P1, and we are then done. Now, this is a little bit like I said, like computer code, right? else f at P1 is either greater than 0 or f at P1 is less than 0. Those are the only two remaining options. Okay? Now, if f at the midpoint is bigger than 0, right, then it means that the interval that starts at A and ends at the midpoint has the property that f at one endpoint, the left-hand endpoint, is less than 0, and then f at the right-hand endpoint is greater than 0, and that's what we want. Okay, so in the case that f at P1 is bigger than 0, we are going to choose the interval from A to P1 to be our new smaller interval, I2. Okay? Otherwise, okay, f at P1 is strictly less than 0, in which case the interval that goes from P1 to the right-hand endpoint, which is B, which is equal to B1, that interval has the property that the function at the right-hand end, or left-hand endpoint, sorry, is less than 0, and the function at the right-hand endpoint is greater than 0. And in that case, that interval from P1 up to B equal to B1 is going to be the interval we declare to be I2. Okay? So let's write that down. So if f of P1 is bigger than 0, we will set I2 to be equal to, well, we'll always label these things. The I sub kth interval will always be A2, B2, but we need to define what A2 and B2 are, and in this case, A2 is going to be the original left-hand endpoint, and B2 is going to be P1. And then if, instead, f at P1 is less than 0, let's erase the rest of this here. If f at P1 is less than 0, set I2 equal to, say, A2, B2. Okay, and in that case, when f of P1 is less than 0, then an A2 is going to be P1, and B2 is going to be B1. Okay? The point of doing this is that in either case, f at A2 is less than 0 is less than f at B2. Okay? So what we have done is we found a new interval, I2, equal to A2, B2, and it has the same property that the original interval had in terms of f, namely that f at the left-hand endpoint is less than 0, f at the right-hand endpoint is greater than 0. Okay? Now, we turn the crank again, and I'm actually going to go through the process of writing down exactly how we find I3, just so we'll see it one more time, and hopefully it will sink in. Okay? Maybe I'll squeeze it all into one board here. So basically there are three possibilities, right? So let's find the midpoint. So let's set P2 to be equal to the average of A2 and B2. Okay? And then there are three possibilities. Either the function is equal to 0 at p2, the function is strictly greater than 0 at p2, or the function is strictly less than 0 at p2. Okay, so if f at p2 is equal to 0, once again set c equal to p2, and then we're done. The whole process terminates. Okay? But otherwise, if f at p2 is bigger than 0, then, well, remember that f at a2, at the left-hand endpoint, is strictly less than 0, and then you would have f at the midpoint is strictly bigger than 0. So that's the interval you want, the subinterval you want. Okay, then we'll set I3 to be equal to, we'll label it A3, B3. Okay, which is then equal to, well, it's going to be A2, P2. And then finally, if f at p2 is less than 0, once again set, well, let's just put it this way, a3 equal to p2 and b3 equal to b2. Okay? Right? So in the case that f at p2 is bigger than 0, choose the first half of the interval I2 to be our new I3. Okay? If f at p2 is less than 0, choose the second half of the interval I2 to be our new I3. And then finally note that now once again, f at a3 will be less than 0, will be less than f at b3. Okay? So what we have done is once again taken an interval, a closed bounded interval upon which f is defined, we have chopped it in two, and we have chosen the half of that interval which we can guarantee still has the property that the function at the left-hand endpoint is strictly less than 0, and the function at the right-hand endpoint is strictly greater than 0. And our ability to do that is predicated entirely on the idea that the midpoint, the function was not equal to 0 at the midpoint. Okay? So, then, continue ad nauseum. Keep doing this. So you would then take I3. You find the midpoint of I3, okay? And then you ask yourself, you call that P3, and you ask yourself, is the function f equal to 0 at P3? If it is, great. Call P3C, and you're done. If not, you're going to be in this situation here where instead of P2, right, you're going to have P3 there, and you just follow the same formula. Okay? So if you keep on doing this, one of two things is going to happen. Either, eventually, after subdividing this interval enough times, you're going to get lucky, and one of these midpoints, somewhere down the line, is going to have the property that the function f is equal to 0 at one of these midpoints, say p sub k, in which case, great, you're done. Or f is never equal to 0 at any of those midpoints all the way down, and you will wind up with a nested sequence of closed bounded intervals with some nice properties. So I will explain that now. All right. So continue until either, these are the only two possibilities, A, f at p sub k is equal to 0 for some k whence, there it is, my favorite word, whence c equals p sub k, and we're done. Or B, we get a sequence I1, oh dear. We get a sequence I1, I2, and so on, such that one, I sub k is equal to a sub k, b sub k. 2, let's say f at a sub k is less than 0 is less than f at b sub k. And finally 3 is that if you look at the length of that kth interval, so that'll be b sub k minus a sub k, well, how long is it? Well, you've been chopping the interval in half over and over again, right? So this is going to be 1 over, I guess, yeah, 2 to the k minus 1 times the length of the original interval b minus a. Not so important what the formula is. The main point is that the lengths of these intervals is going to 0. Okay? So, with this iterative procedure, which I have detailed the code for, okay, you arrive at this situation. Either some midpoint has your function equal to 0, in which case you call that midpoint your point C from the formula, from the theorem rather, and you're done, or you wind up with this sequence of nested closed bounded intervals, okay, and we know something about that situation. So we're going to assume, so if B, then the intersection of all of those closed bounded intervals is equal to a single point, which I will suggestively call C. Okay? So that's by the nested intervals property. Okay? So that's the combination of the nested intervals property, right? So these are closed bounded intervals, they're nested, and the lengths of those intervals is going to 0. Moreover, as must be the case, the supremum of the AKs is equal to C is equal to the infimum of, well, let me put it another way. The limit of the AKs is equal to C is equal to the limit of the B sub Ks. Okay? So it turns out that whenever you have a situation with the nested intervals property, both of these limits are going to exist, okay, because the AKs are increasing, the BKs are decreasing, the BKs have a lower bound, these guys have an upper bound, so they converge to the sup here, the inf here. But since the intersection of all these intervals is just a single point, in fact, they both converge to the same thing. Now, we're going to use this guy here. So I basically used the nested intervals thing, so let's get rid of that. Now I'm going to make use of part 2 here. Right, and I've also used part 3 here. That's how I got the nested intervals to have a single point for an intersection. So how do we use part 2? So by continuity, we can go ahead and apply the function f to all the AKs, to C, and all the BKs, and these limits are still good. Okay, so that f of C is equal to the limit of f of the AKs, and is also equal to the limit of f of the B sub k's. And then finally, by part 2, below here, every one of these f of AKs is strictly less than 0, which means that the limit, at best, can be 0. This is going to be less than or equal to 0. This limit is less than or equal to 0. By 2, the limit of the f of AKs is less equal to 0. And by a similar argument, right, every one of the f of BKs is greater than 0, meaning that the limit of the f of BKs is greater or equal to 0. Well, each of these two limits represents the same number. You're saying that this number is at once less than or equal to 0 and greater than or equal to 0. There's only one number, which is both less than or equal to 0 and greater than or equal to 0, namely 0 itself. In other words, these two limits are equal to f of C, and f of C is equal to 0. Thus, f of C is less equal to 0, f of C is greater or equal to 0, which implies that f of C is equal to 0. And that concludes the proof of the theorem. Okay? So that is the location of roots theorem. And in fact, really what it is just the intermediate value theorem, kind of in disguise. Okay? So that's the corollary that we're going to explain now. So corollary is the intermediate value theorem. Okay. And it says the following: suppose that the function g, or whoops, sorry. Sure, why not? Okay, g from a to b, from the closed bounded interval a, b to r satisfies that g at the left-hand endpoint is strictly less than k is strictly less than g at the right-hand endpoint for some real number k. Okay? So at one end, you're less than k. At the other end, you're greater than k. It follows then, satisfies this. And, importantly, that g is continuous on the entire interval from a to b. Right. Then there has to be some point in the open interval from a to b where g is actually equal to k. Okay, it actually has to take that value k. Then there exists some c in the open interval from a to b such that f of c is equal to k. All right, that's the intermediate value theorem. Continuous function on a closed bounded interval. The values of the function at the endpoints bracket some number k. Then there's got to be some numbers somewhere in that interval where the function is actually equal to k. You can't skip any numbers on the way. You're going to get from g of a to g of b and k is in between, then k is a stop along the way. G, not f. Sorry. This is really hard out here. I don't even have the luxury of having that one annoying student that always points out the little mistakes you make at the board. I'm going to point them out for myself. Anyway, hopefully one day we will all be back in the classroom. One day. Yeah. All right, so let's prove this. It's a very easy consequence of the location of roots theorem. Okay. So, proof. Let's set f of x equal to g of x minus k. Right? Well, g of x is a continuous function, and k, the constant function, is certainly a continuous function, and we know that the difference of two continuous functions is, again, a continuous function. So f is continuous on AB. Continuous on AB. Right? Then, well, f of A is equal to g of A minus k, which is less than k minus k, which is less than g of B minus k, and of course k minus k is better known as 0. And this is f of B. Right? In other words, you just take the continuous function g and you shift it downward by k, and now what you've got is a new continuous function f, and f has the property that f of A is strictly less than 0, is strictly less than f of B. By location of roots, there exists a C belonging to AB, the open interval, such that f of C is equal to 0. So it's then clear, right, that G of C must be equal to K at that same point. And that's it. Okay, so you just take G and you shift it downward by K, and then you apply the location of roots theorem, and that will give you the point C where F is equal to 0, and therefore G is equal to K. All right. You know, I wouldn't say I enjoy going to the grocery store. I've gone like twice in the past 4 weeks, basically, but I absolutely had to go today, or else I would have had a mutiny on my hands because we were out of frozen fruit, which would have meant that the smoothies stopped flowing in the morning, and that would have caused a mutiny, right? It's like Dune. The spice must flow. If you don't have the smoothies, you're in trouble. It's hard enough keeping 2 kids home for a month. So I went to the grocery store, and I don't know if you've been out there, but depending on the day and depending on what the news has done and depending on how paranoid people are feeling, the stuff that is and isn't on the shelves out there can be kind of wild. You never really know what you're going to get, which makes it kind of exciting, but also means you can't really plan anything. You just got to go and see what they have. But what they did have, to my great excitement, was turkey. So somehow out of the blue, this is one thing that was still, available in the supply chain. So why not? It's not Thanksgiving, it's not Christmas, but that doesn't matter, right? Because it's turkey, right? There are people who wonder what it is they're going to do with themselves when they retire. I don't have this problem because I am planning a 17-volume treatise on Turkey as a religious experience. I cannot decide if it's coming before the 17-volume treatise on steak or after it, but it's going to happen. So, upstairs in the sink, there's a bird thawing. So, if one of your unfortunate parents or even you has to go out, keep an eye out. There might be turkey out there. Okay, let's see. So we've done location of roots. We have done intermediate value theorem. Oh, one more corollary that I won't even bother going through all the details of, but it's worth mentioning. If F, so putting together a bunch of the results we've got so far, if you have a continuous function on a closed and bounded interval, then F applied to that whole closed bounded interval, in other words, the range of F on its domain, is a closed bounded interval. Okay? So continuous functions carry closed bounded intervals to closed bounded intervals. And, if you go on, if somehow I haven't turned you off mathematics completely, then you may go on to discover that this is actually a very sort of baby version of a very general fact, which is that the continuous image of a compact set is again compact. I don't know if you remember way back, but I was talking about the possibility of a set being small in some sense, and this is an example. The idea is that if you cover this little guy, you cover it in scales, little tiny open sets, then no matter in what way you cover it with open sets, you only ever needed finitely many of them, which is pretty nifty. That's what makes it a compact set, and the continuous image of a compact set is compact. But for you, for the exam, all you have to remember is what's written right here. Okay? So, that concludes, let's end section 5.4. And then this is the reason why there's only one page of notes that I posted on Blackboard for today, because these notes, in fact, are all from what I posted on Monday. And even though I only posted one page of notes for today, we are still not going to get through that whole one page. But we're going to start. So we're going to start working on section 5. That was 5.3. Now we're moving on to 5.4. Yes. And the title of 5.4 is something called Uniform Continuity. Okay? So this is like an enhanced version, if you like, of continuity. A better thing to have happen to you than simply for your function to be continuous is for it to be uniformly continuous. Okay? So let me just say some things before we actually write anything down. Let's draw a picture. Let's draw two pictures. Start with a very simple picture. It's just a picture of the function. No. There we go. Sorry, my screen cuts out on me, which is, I don't even know. The camera light stays on, but my screen cuts out on me, so I can't see what I'm doing. So that's the only reason I come in and fiddle with the computer every now and again to make sure the screen stays on. So here's a very simple picture. It's a picture of our friend, the function f of x equals x. And if, so we know that this function is continuous, right? And if I wanted to prove continuity, the idea would be that I take some horizontal tube whose width is, I guess it would be 2 epsilon, right? And I ask the question, how close to C do I have to be in order for me to look up and land on the function somewhere inside that horizontal tube, right? So you can kind of draw dotted lines here and here. And roughly speaking, you can find this little open set around C. And the width of that open set around C, or the radius of it, is going to be delta, right? So you're given epsilon, you find delta. But what I want to point out is that because this is such a nice, simple function, the relationship between, how, like, if I want to be within 2 epsilon up here, how close do I have to be down here? That's the game. Well, the game is very simple for the function f of x equals x. Right? If you want to be within epsilon up here, all you got to do is be within epsilon down here. It's a direct one-to-one translation, right? And importantly, it doesn't matter which point C you're considering. Okay? So C could be anywhere here along the x-axis. It would still be the case that if I gave you epsilon and you needed to be within epsilon of f of C, you would still only need to be within epsilon of the point C on the x-axis, no matter where C was. Okay? The function is very uniform in some sense. It looks the same everywhere. Okay? Let's contrast that situation with this function, let's look at f of x is equal to 1 over x. Okay, it looks like this, right? And let's pick a couple of different heights. F at C1, F at C2, and of course we'll go across. That will correspond to a point C2 here, I guess to a point C1. Let me even lower this. Let me put it way down here. Let me put it down there so we get a little further over. So there's my C2, and there's my C1. Okay, all right. So if I want to be within epsilon, some horizontal tube of C2, I don't have to be particularly close to the point C2. I've got all this latitude in here. As long as my x value is somewhere in here, and when I go up to the function f of x equals 1 over x, and go across to the y-axis, I'm going to land somewhere in that horizontal tube around C2. Okay? However, if I take the same width of tube way up here, then I am going to land, how close to C1 do I have to land? Well, super close, right? It's a lot harder. I got to stay really, really, really close to C1 to make sure that my function values don't change too much from f of C1, okay? So the function then is what it turns out is called not uniformly continuous. The function is not uniform, meaning it does not really look the same everywhere. It just gets somehow steeper and steeper and steeper as we head towards 0, and the situation gets more and more difficult. You know, the larger the f value you're concerned with, the closer you have to be to the corresponding x value in order to guarantee that you're in a little neighborhood around the f value. Okay, so they're two very different functions. This one looks the same everywhere. This one certainly does not. Okay? So the idea of uniform continuity is this. A function is uniformly continuous if, for the whole domain all at once, if I give you an epsilon, meaning if I give you a little horizontal tube around a function value, like here, like here, like here, you can tell me how wide the vertical tube has to be, and how wide that vertical tube has to be does not depend on where you are in the domain. Okay? So over here, it didn't depend where you were in the domain, right? Take the width of the horizontal tube, tells you the width of the vertical tube, no matter where you are. Over here, not so much. Take the same width of horizontal tube here and here, and the width of the vertical tube over here could be really wide, over here super narrow. Okay? So it doesn't have a kind of uniform behavior. All right, so I haven't given you the official definition, but I'm trying to give you the flavor of uniform continuity. So the idea is that in our definition of continuity, usually continuity is a pointwise concept. You ask if a function is continuous at a point C. Okay, and then given epsilon, you find delta. But that delta depends not only on epsilon, but in fact, implicitly on the point C. Here, for uniform continuity, it's going to be the case that you get epsilon, you can find delta, and delta no longer depends on C. Okay, this will work anywhere in the domain. And that's the notion of a uniformly continuous function. So we will give the details of that definition, some more examples, explicit details for those examples, and so on, starting in the next class. So stay safe and wash your hands.